So when a patient arrives at a trauma center, they are first put into trauma bays, where they wait until the patients are stabilized. Then after being stabilized, the patients are moved to operating rooms to receive a surgery. So let's first look at the server side. And usually in hospitals, in trauma centers, these trauma bays are the most scarce resources. So the patients are put in to trauma bays immediately after they arrive at trauma centers. But when all of the trauma bays are full, then the hospital goes on diversion status. When all of the trauma bays are full, the hospital can no longer admit any incoming patients, and they close their system, and all of the newly arriving patients have to be redirected to other hospitals. And on average, it takes 2 hours for a patient to be stabilized in trauma bays, and after this, they will be moved to an operating room.
Would we need the standard deviation of P?
So actually in this chapter, we don't really need the standard deviation. So what does this mean is that we don't really need to know what distribution the processing time follows, because the formula that we're going to use to answer our 2 major questions does not depend on the distribution of the processing time. Okay? So we don't really have to worry about the standard deviation of the processing time. Thanks for asking this question. So that's the server side. And then we also need to look a little more on the demand side. So patients, trauma case patients come in every 3 hours. So A is equal to 3 hours. So this is the inter-arrival time. But whenever they see this system being full, they are redirected. They're blocked. Right? And although I don't have this here in the slide, we again have standard deviation of A being equal to 3 hours.
In this class, the standard deviation of A will never change from A.
Yeah, yeah. So CDA is equal to 1. But actually for, in chapter 9, I won't really directly ask you to figure out what CBA is, because you'll see that you actually don't need this information to answer our 2 main questions. Right. So this is what's going on. And let's go back to our 2 main questions. What was the question that we were interested in? We wanted to figure out what is the probability of customers being blocked, right? And let's call that probability of a patient being blocked PM. Right? So we first want to know how often a patient is being blocked. This is also the probability of the hospital being on diversion status, right? Also, this is the probability of all 3 trauma bays being occupied. Okay? Here, N is 3. We have 3 trauma bays. And after figuring this probability of customers being blocked, we want to figure out what the resulting flow rate is. Right? We know that this is going to be different from the demand rate. Although customers come in every 3 hours, we'll be blocking some patients, and then at the end of the day, the number of patients that will be served will be different from the number of patients that are coming to the system. Any question about the setup? Before we dive into solving these, let's first look at what the demand and the capacity, average demand and the capacity for this system is. Okay? What is the average demand for this system? Demand depends on the customer's arrival process or the patient's arrival process. And we know that one patient comes in every 3 hours, right? So the demand in patients per hour is equal to 0.333 patients an hour. How about the capacity? You know that each trauma bay can serve one patient every 2 hours, and there are 3 trauma bays. So this is 3 times one patient every 2 hours, which is equal to 1.5 patients per hour. So again, you can see that we have enough capacity to serve the demand on average, but we will still have positive PM. Right. So in order for us to find what PM is, we have to learn a new methodology to compute that.
Sorry, where did the half come from again, capacity?
Half comes from the fact that P is equal to 2 hours. So for each trauma bay, the trauma bay can serve one customer every 2 hours. So half a customer an hour. So just as we've learned the new way to compute TQ in Chapter 8, in Chapter 9, we have to learn a new methodology to compute PM. But thanks to a person named Erlang, this person has figured out the formula to compute PM. And also, we actually have a table of this probability that we can just look up to figure this probability out. And this table is in your textbook. It's Appendix B, and it's on page 189 to 191. Also, if you don't have the textbook, you can Google it up. If you just put Erlang loss probability, then you will find that out. And also, if I ask you any question related to this probability in the exam, I will provide the table for you. Okay? So, but we still have to learn how to read this table.
Sorry, on the homework, we'll need to use the book, right?
Yeah, for the homework, you can use the book or you can use the table online. All of the tables have the same values. So let's learn how to read the table. In order for us to do so, we have to first know what this probability, what are the factors this probability depends on. Okay? So this probability depends on, first of all, the number of servers. We already know this, right? There are 3 servers or 3 trauma bays that treat patients. Then another factor this probability depends on is a variable R. We're defining this variable now, and this is defined as M times the utilization, the implied utilization. Okay? And we know that U is equal to P over M times A. Right? We know that U is equal to P times M times P divided by M times A. Right? So R can also be rewritten as P over A.
What is R?
R, so let's, yeah, it's a good question. Let's see what R represents. So R is M times U, right? We know that when we go back to what we learned in Chapter 8, in Chapter 8, when we learned how to compute IP, right? So utilization represents what is the average number of customers there is in each server. Right? And so U is the average number of customer or patients being served in each server. And when we times times it by M, then we get the average number of total customers that are currently being served. Right?
Which
So,
is R.
which is R, yes. R is N times U. U represents the average number of customer in each server. When we times it by the number of server, it gives us IP. So you can sort of think of R as IP. There is actually a subtle difference because now we are using implied utilization here, which I have not explicitly talked about because I didn't want to confuse you. Okay? But you can think of this as being equal to IP, right? So R, again, R is defined as N times U, and we can compute that by dividing P by A. What is P in this example?
2.
P is 2. A is 3. So on average, there should be 0.67 customers in the trauma center here for 3 trauma bays. Right? Okay. And now with these 2 values, we are ready to find the probability of a patient being blocked. And we actually call this probability PMR. Okay, so if we know M and R, we can find this probability out. Let's now actually look at the table to see how we can find that
Sorry,
probability.
can you move back real quick?
So, yeah, there we computed the utilization.
Right, thanks.
Any question? Right. Let's actually look at the table. This is the Erlang loss table that is on the back of the textbook. So in the Erlang loss table, the columns represent the number of servers. So the columns have the value of M. The M can be 1, 2, 3, 4, 5, right? And the rows give you the values of R. We know that our R is 0.67, so you just need to look for the row that corresponds to R being equal to 0.67. Right? So this is the row for R equals 0.67, and then you look for the column that corresponds to M being equal to 3. Then when you find the probability at the intersection of the row and the column, you'll find this probability. And it says that it's equal to 0.0255. So what does this tell us? This tells us that the probability of this trauma center blocking a patient is equal to 0.0255, which means that with 2.55% of the time, this hospital will be on diversion